Let's do some definitions. Electromagnetic wave. It's a wave, obviously, which propagates week 8. How do electromagnetic waves propagate? What makes electromagnetic wave wave? No, it hasn't got a medium. Electric and magnetic fields. So that's the answer for that one. Faraday dark space.
There's a striation after the cathode Crookes tube. This occurs while electrons are accelerating and don't have the velocity to hit the gas particles.
Yeah, except there's a word in there which would get it wrong for you. That word striation.
I thought it was what?
Well, striations imply alternating dark and light areas. So just be careful of that one. So it's actually an area, as you say, in a cathode ray tube.
There's nothing there, like I can't see anything light.
Well, you can simply say which is dark. And where's it between?
Between
The cathode and the positive column.
What does the EMB stand for?
Electric and magnetic.
between the let's go to here is between the negative and the positive column.
That's close enough if you're in an exam.
Yeah.
Area in a CRT cathode ray tube, which is dark, and should be a comma, between the cathode and the positive column. Ionised?
Ionized is when electrons are knocked out of it.
Yep. Particles which have lost or gained.
Oh, so what if you like this? These are I think they're knocked out before the final.
Yes, that would do.
Yeah, so
Don't forget, it can be adding charge. It doesn't have to be removing charge. In the case of the cathode ray tube, it is removing charge. Okay, the canal ray is the stream of ionised particles in a cathode ray tube. Well, it's actually positive ionised particles.
I've got that too. Yeah, like these ones. I've probably got about 10 of those.
So, what it was observed by someone like her, I can't remember the name, that's standard, but they observed that where you got the cathode rays going one way, you could see that there was a stream of positive particles going the other.
So I just wanted to mention this, that there was a point, Silver's point in main idea 4 of motors and generators that we didn't cover.
What was that?
Assess the development of transformers on society.
Okay, I did talk about that.
Yeah, we did assess
And-
the development of basic generators.
Yeah, and what I said when we got to that point was that in our electrical grid, you could not run it without the transformers, and so consequently, it's exactly the same answer as the previous dot point.
But it wasn't the same. Like my textbook said it was a bit. My textbook said it was different. The other sources I used, they all said it was a different answer.
Okay,
Because transformers allow, like for industry, they allow a greater range of voltages to produce, meaning there's less chance of.
yes, but the effects on society for us are exactly the same thing. I mean, I didn't go into detail agreeing. If you want a detailed answer, I can put one out for you. Yep. No, that's fair enough. X-ray.
X-ray is band of electromagnetic radiation that is damaging to human tissue.
I said EM wave, but using the
Use
It's used medically also.
Between, what's the frequency between for it?
at 550.
I don't mean actual.
Oh,
On the bands, you go radio, then what?
radio, then
Radio.
microwave,
infrared,
infrared, visible, UV.
X-ray.
So it's between UV and gamma.
So did you hear about the discovery of Kepler 184?
What's that?
Planet,
Yes, I did actually.
planet.
Kepler 184. Isn't Kepler the telescope?
Yeah, it's a telescope.
It's
It's 20% larger than our sun and 20% more careful for this. So the way the same size. So
It was
they don't always say how much.
was 338 days.
It's years the same time.
No, it's slightly. It's like 388 or something like that.
We need to move on here. This is a little bit of a repeat, what I've got on the board, in some ways, of what we did back in
Electricity in the home.
lectures 9. And you would recognise you have two plates, and if you charge them up, there's going to be electric field between them. And you can represent the electric field by vector lines of force, which are vectors, and because it's a uniform charge on the two plates, they should be evenly spaced, they should be parallel, right? You all know that. And you know if you place a charge in there, that, so I put a positive charge into this particular picture at this point, it is going to
Experience.
and be accelerated which direction?
Yeah.
It'll go downwards until it hits the plate and rests on it. And at that point, in that journey, where will it have its minimum potential energy?
In the middle. At the start? At the end.
Minimum. It will move to its area of last potential, and that'll be its area of highest potential. So if I take a charge off this plate, and I want to move it back that way, I'm going to have to do work on it. Aren't I? Work is? What's our definition for work? W equals FD. So I will have to apply a force to that charge to push it back against that field, and it will gain some potential. Okay? All right. So that's pretty easy. We all understand that. That's nothing new. Now, what we do know, as I said, if the work done on anything is the force times the distance we travelled it through, right? But we also know for an electric field, we can measure the size of the force as be applied to it, can't we? Yes? Does anyone remember the formula that defines what a size of an electric field is? Equals the force per unit charge. So therefore, in this case, force, if I rearrange that, I'll take the F equals EQ. That means that bit, can be subbed into the here. So I end up with F equals E Q D. Now, the other thing that we know is that when you gain potential in a field, we have a word for doing, in an electric field, we have a word for doing that. Okay, and it's a word that we learned back in electricity at home. What would that word be? Voltage. And we know, well, you don't quite know, but it's actually true that that voltage per unit charge is actually the work that you do on it. So on this side, I can put in the equation VQ equals VD, Q, and of course our Q's drop out, which means that the voltage, or the potential, equals the strength of the electric field times the distance we move it in there. So that if you know the voltage between the plates, right, you can work out the voltage of the particle by how far you have to move it in that electric field between those two plates. All right? Very simple formula. The reason I'm introducing this to you now is quite simple. While it just looks like a bit of information out there, it's actually something that Thomson used when we looked at his experiment to work out what the cathode rays were. It's something that Thomson used to work out what these things are. Now, what this says, if I fire a charge in between these plates, it's going to experience a force. So it's going to be accelerated. And what sort of path, Marnie, do you think it's going to follow? Follow an arc, so it will curve down if it's a positive charge. Okay, quite obvious. And we can measure the size of the voltage, and we can measure the distance it falls, and we can work out the strength of the electric field in it. Okay, we can do stuff with that. May not be super exciting to you guys, but it was important for Thompson and his work. Yeah. Yeah, what's that?
But, when we're doing this, why do we always say electricity goes across the side? I know you said
Yes. Yeah, because the syllabus reflects the way that Australian physics is worked out. So the reason that it was first said that way around was because Benjamin Franklin decided it was the positive that charge moved. He's one that actually named charges as positive and negative in that sense. And the maths was worked around that. Now what you can do is you can actually rewrite all the formulas, putting minus signs in them instead of plus signs, and working it through and getting all new formulas for it. And there are people to do that. Actually, there's a whole branch of physics that does that. That's fine. But in Australia, we just happen to have stuck with the tradition. So it's just tradition. Okay. Now, in this case, you have a series of questions there which asks you to compare the strengths of various electric fields. Okay. Now, so Jason, you can help me out here. What can you tell me about the electric field at X and the electric field at Y? Don't know? What can you tell me about the electric field between two plates which have a uniform charge on them? They've got exactly the same charge. Well, in this case, they will be going upwards. But no, the potential, not the potential difference is strongest there. But what can you tell me about the electric field? It's uniform because they're uniform arrows. They're evenly spaced. So the electric field through that space is identical any place in it. So X and Y are identical in terms of the electric field.
What about the triangle ones? Does that mean that as it gets closer towards the centre, it gets stronger? Because the lines get closer together?
Yes, that's right.
So for that B one, would that mean that Y would have more potential?
That would have a higher potential, right? The voltage will change on it, but the electric field is the same. Now, let's have a look at question F. So Riley at the back, what in F you have X on there and Y there. What are they going to be? Are they going to be, will the electric field be the same, less or more at X compared to Y? Same, because the field looks exactly the same, the field lines are exactly the same, the lines of force are the same, so they're going to be the same. Which means that, Josh, if I look at X and Y in diagram A, are they going to be is the electric field going to be the same X and Y or different? It's the same. They're the same distance from the centre, so they're in the same part of the field. It's supposed to be the same distance from the centre, so they'll be the same.
So if they're a different distance, they'll experience.
But not in case B because it's uniform. But in that one, if that one was close in and one was further away, because the field lines of force spread out, it means electric field changes. The same as in D and C and E there. Now, and you've got some questions around that. Be careful about this, that you understand and know what changes with where the particle is. In this case, for question 7, calculate the strength of the electric field at these points. Right? Calculate the strength of the electric fields at point X, Y and Z. What can you tell me about the electric field in those points, even without having to do calculation? They're all the same. But if I was to calculate the potential at those points, which is the voltage, it would be different. And they've actually had a question almost identical to that in HSC to catch people out about whether they understand what electric fields are compared to voltages. Yep. Yep. Okay. The other thing we have, which you're going to learn about, and in your sheets there is another formula you need to know. And this is the one that Marnie, I think, someone spoke to me about it. That's Mr. Fogwell's favourite formula. Yes, at the study day. F equals QVB sine theta. You know, a force, a particle moving in a magnetic field will experience a force. That's what that formula says. And that's a formula you need to know. A particle, Q, a charged particle, Q, moving in a magnetic field B, and V is the moving bit, the velocity, experiences a force. Now this is straightforward, this is straight maths, just another formula. The reason you've got it, it's very simple. When it came to, who is it that's going to do you're going to have to learn the great experiment about? J.J. Thomson. J.J. Thomson also used this information to do some calculations to work out the nature of that charged particle. Okay, so that V equals ED is important to Thomson, as was this F equals QVB sine theta. They worked those things out and he had that as a tool for him to work with. Now, one of the things you might ask yourself is, which way is the force acting? You have to be a little bit careful about this. Now, you remember the right-hand rule that I taught you before, the FBI? Well, you can actually use that rule. Now, you'll find in a lot of textbooks, and I know Jack will probably pull me up about this, you'll find an awful lot of textbooks, they'll teach you a second right-hand rule to work this out. I'll just say this for Jack's benefit. We've got Mr. Fogwell's favourite equation. Yep, so a charge moving, which is Q is the charge, V is the moving velocity, in a magnetic field B experiences a force F, and it's sine theta. Now, that sine theta can be important. We also want to know the direction of the force. Now, I taught you a right-hand rule. In lots of textbooks, they actually will teach you a second right-hand rule. I don't do that for the simple reason I think that if you have 2 or 3 different hand rules, they can get confusing. But what you can do, very simply, if your palm is F, your fingers are B, and your thumb is I, okay, the force is what you want to find. B is simple enough. Now, the trick is I. You need to know which way to point it. Now, a current is the motion of a what type of particle? Charge. So there's what sort of charge?
Negative.
Positive. It's a conventional current, positive. So there's a positive charge moving that way, which means the current moving upwards, therefore the current is up. The other way.
Force is going against the page.
Well, let's just check it out. If B is that way, I is up, the force is in to the page. Easy. Right, if it's a negative particle, like in question C, it's moving that direction, right, but it's negative. So F, B is up, I will be in the opposite direction. No, remember, it's a negative charge. Negative charge is going that way, which is the equivalent of going to the right, which is the equivalent of a positive charge going left.
What happens if the positive charge is going that way and the current and the magnetic field is going that way? You can't make your thumb do that and do that.
If you can't get it on your thumb and finger, it means there's no force acting.
Oh wait, no, there is. Yeah.
Did you use the left-hand rule in that case?
No. Oh, actually it would work with your left hand.
Because your left hand's opposite to your right.
Yeah, well actually what Steve Fogwell did is he got them to change the hand round. He had positive one side, negative the other.
Oh.
Right, he did it that way. Now guys, I'll just say for your information so you get it, when Steve Fogwell did it with people, he used this rule, but what he did was he said, see the negative signs in your fingers? You can, right? And he used that to work out which way up your hand is.
This way, but it said something about it going this way as well.
Well, what he says essentially is that if it's a positive charge, it'll go one direction. If it's a negative charge, it goes the opposite direction. That's all the force. Now, try to set you loose with some formulas. There is a really, really important thing to be careful of here. I want to show it to you. I'm going to draw a magnetic field on the board, just representing it by some field lines.
Cody didn't even show up. Yeah.
And you get a charged particle, right? Now, let's make, we'll put a charged particle coming into the field. I'll make it positive at 1 coulomb. It goes like that. And I'll put an angle there of 30 degrees.
How do you know which angle to use
like
We made it up.
in torque, it's the angle between the plane and the coil. If F equals Bill sine theta, it's the angle between, it's that angle. Is it the same one?
Now, I want you to look at that, and then I want to show you another one, and I'll show you. That's what I'm going to do. Imagine now we're looking at a magnetic field going into the board. I'll make it easy. I'll make the magnetic field 1 Tesla.
Sine 30 is equal to
Now, this is a uniform field. I'll make the velocity of the charged particle, let's make it really easy, 10 meters per second. In this case, what I'm going to do is I'm going to put a charged particle. It's going through there. It's 1 coulomb. The angle there is 30. And it will be going in at 10 meters per second. Now, the formula that you want to use to work this out is
F equals
F equals QVB sine theta.
What's Q set for?
Q is the charge, V is the velocity,
These make
B is the magnetic field strength, and sine theta is the angle. Quickly,
1 times 10 times 1 times 1 on root.
how much? Okay, that's A. What about B? What's the answer?
You've got 1 times 10 times 1, so it's 10. You tried to check us that, sir, didn't you?
Let's see what you go for the answers. Very well done.
Instead of doing what Jack did, the 1 over root 3.
You just do something.
Just do sine 30. Now, pardon?
How is that in ratings, though?
Where sine
It's 1 over 3, actually.
yeah, someone would answer 1000.
Okay, there we go.
No, it's
It's a half. So,
What's the line of soul? No one's sorry.
Oh, yes.
yeah, it is.
moving on, let's see why this answer is correct and what's different. If you think about this one, if you think about B, let's concentrate on that first. The magnetic field is going into the page, right? That's what the X is. The magnetic field is going into the page. Remember, the X means it's like look at the end of an arrow going into the page. Count of dots coming out. Now, if you think about this, if I use a pen to represent the wire, what angle is it? There's the pen, the magnetic field's coming out that way, or, going in that way, I should say. So what is the angle between the pen and that field? What happens if I make it that way? Doesn't matter which way I rotate it around, it's always 90, isn't it? It's like, remember, it's a little bit like the wire on the rotor or on the coil in a motor. So as the coil was swinging around and around, it was always at 90 degrees to the field. In this situation, it's always at 90. But this one, clearly, there is an angle.
How do we find the direction then?
How do you find the direction? In what way?
Well, it's experienced force of 5 newtons in the direction.
Yeah.
Oh, which direction? Well, again, okay.
Oh, wait, I know this. It'll be like that. Oh, no, you do it.
No, because you can't do that. Well, you can do it in the second one because into the page, current.
It's the, actually what it is, it's the projection of that part of the vector in here. So in this case, you're going to use, it's a positive one, so it's going to be thumbs up. And B is that way, so it's going to curve into the board.
But current, where's the current?
The-
Current is going, like,
Yeah, but what I'm saying, Jack, it's the projection of that
yeah, the 90 degree.
90 degree component of that force. Okay,